Good evening, everybody, and welcome to the ATX Science Olympiad Regional for 2021 award ceremony. We're so excited to have all 36 teams competing yesterday and today, and we're very excited to announce our speakers as well as who won each division and event. ATX Science Olympiad Regional for 2021. Next slide. Ceremony. We're so excited to have all. These are your MCs and behind the scenes crew for today. I'm Rebecca Schooler. I'm a biochemistry major here at UT, and I'll be graduating in class of 2023. This is Isha Borker from finance of class of 2022, as well as Fedor Fedor, I just killed your name. Aglayamov, who's running our computer screens today, as well as Daniel Hahn. Next slide. This is pictures of the rest of our team who help out behind the scenes, running events, as well as helping coordinate a lot of our online awards and whatnot this year. Next slide. Give us all a follow or a shout out on social media. We have a TikTok now, and we'll be trying to post more content this year of our team so you can get to know us individually. And we also post a lot of content on our Instagram. So we post the link to this live stream and a lot of our giveaways and fun content like that. And you can find us at atx.scioli on both. We also have a Facebook page. So yeah, give us a follow. Next slide. And I'll tell you about our giveaway. So for the spring competition, we have a merch giveaway for UT Merch Hookem. So the three things you need to do are be following our Instagram account, repost this this screen on our page. You go to the page and you hit share to your story, and tag us, and then tag a friend in the comments, and this will automatically enter you in our merch giveaway, and we'll be announcing the winner tomorrow. We're trying to give everyone today a chance to enter. Yeah, so we've got some exciting stuff, and we'll be posting the winner tomorrow night. So yeah, go ahead and enter. Next slide. Today we have two wonderful speakers here to talk to you guys. We have Dr. Charles Jackson from the UT Institute of Geophysics, and he'll be presenting first. And then later on, we'll have Dr. Paola Passalacqua, and she is from the Cockrell School of Engineering, and she'll be presenting second to you guys. Next slide. We have a tiny URL code here, as well as a QR code, so you can use your phone to scan this, and it'll bring you to a Google form to enter questions that we'll read live after each professor or each doctor presents. So yeah, so please enter those and ask away, because we'll answer 3 or 5 at the end. Next slide, and I'll introduce Dr. Jackson. Dr. Jackson works on problems concerning the use of data to test physics-based numerical models of the atmosphere, ocean, and cryosphere, particularly for phenomena involving their interaction. Some example problems he's worked on include abrupt climate change, which we'll be presenting on today, and the origin of ice and climate cycles, and the projections of future climate and sea level rise. So please give a warm round of applause at home for Dr. Jackson.
Hi, everyone. I'm sorry that I can't see you right in front of me, but so I'll give you a kind of a introduction to myself, my career path, and I will be talking about abrupt climate change, and it's kind of related. I'll talk a little bit about the geosciences more broadly and about the types of problems that are interesting, including abrupt climate change. So I went to Haverford College. They actually, behind me, you'll see a library. That's from Haverford College. So I majored in physics, and one of the kind of problems I worked on is phase transitions. And that's like, when water goes into ice, that's a type of phase transition. But I worked on that problem there. And I work on phase transitions now as a climate scientist. So there's some sort of continuity there. So then I went to University of Chicago, and graduate programs all have certain types of specialties. And University of Chicago, they have strengths in theory and simple kind of conceptual models. And there's always a place for different types of inquiry in science. And when you're talking about climate, which is very complicated, like there's all these systems of systems, there's kind of a need to have somebody kind of simplify everything that's going on. But after I had that experience at University of Chicago, I moved on to a laboratory, the NOAA Geophysical Fluid Dynamics Laboratory, and that's associated with Princeton University, where that group developed some of the first global comprehensive models of the Earth system. So I learned about large-scale modeling there, and then came to the University of Texas, and where I'm a research scientist. And one of the important points about being at the Institute is that there's a lot of people that go out and make measurements of the Earth system. And early on, when I was at University of Chicago, I had an advisor who basically said, you know, we do all this theory and kind of simplified modeling of the Earth, but really you need to situate yourself at a place that's where they get into the complications of what the Earth is, where they make observations. And so that's one of the reasons why I'm at the Institute for Geophysics, is they make these observations of the Earth. And so it's a lot of fun. So next slide, please. So this time series is one of the most transformative observations of climate that there is. And this is taken from an ice core, a 2-mile deep ice core from the summit of Greenland. And this was obtained just as I was, just before I became a graduate student. And these observations were, let's say, being presented to the theorists around the world, and we were all kind of confounded by what was presented here. And so what you'll see on the left is 80. So that's thousands of years ago, 80,000 years ago, going up to present, which is all the way at 0 at the right. In the last 10,000 years or so, you'll see that this time series is relatively flat. And I should mention that this time series is a proxy for annual mean air temperature. It doesn't have units of air temperature, but basically from the Holocene, which is the last 10,000 years, to the maximum, last glacial maximum. So that's that LGM initials there. So it was about 25 degrees Celsius cooler. So the amplitude there is about 25 degrees Celsius when it goes back into the last ice age. And kind of the most amazing thing about this time series, and which basically leaps out at you, is that the last ice age wasn't always cold. In fact, it was punctuated a number of times abruptly to where it was about 16 degrees warmer at the summit of Greenland. And those transitions were rapid. The ability to resolve annual changes in this ice core are best during the last, let's say, last 10,000 years. And that transition from a relatively cold state to a warm state happened within 3 years. So these transitions were basically sudden. And this kind of went against everything we were thinking about the way climate works. And mostly we think of, you know, when you're on a bicycle, if you want to go fast, you have to put in more energy, right? And your speed is directly related to how much energy, how much effort you put on those pedals. And here is a time series that says that the way that the tropics brought heat to the poles was not like that, like the same amount of effort resulted in the same speed. Is as if it jumped to warp speed and you brought all this heat up to the north all of a sudden. And it stayed that way, that the system had a different way of operating, kind of, let's say, a slow speed and a rapid speed, where all this heat from the tropics made it up to the north. And we still don't quite understand how this occurred. So I will be making kind of an analogy here to phase transitions and asking the question of, does Earth have phase transitions? Next slide, please. Okay, so when we were thinking about these climate change and what are the ingredients of it, we said, well, there needs to be a trigger. There needs to be some way that that initial trigger was amplified by some process in the climate system, and then somehow it needed to stay that way. So next slide. So one way of thinking about these three ingredients is a canoe going down a river, and the canoe gets jostled around by the waves, and the canoe, you know, isn't always a stable boat on a river because, next slide, please. There could be a moment, and we'll call this the trigger, when one of the people seated in the canoe doesn't quite keep balance, and they tip the canoe, and then a little bit of water comes in. So that's the amplifier, right? The water coming in the canoe. And then the persistence is the fact that that canoe might flip over, and it's not going to basically flip to the right side until you get out of the canoe, bring it to the side of the bank, and empty it of water, and bring it, put it back on the water. So it's kind of a permanent state for a long time. Okay, next slide. Now, this is an image from a model, very high resolution, showing water vapor. And I'm using this slide to illustrate basically the functioning of climate. And so most of the sun's radiant energy comes into the tropics and warms up the water. That water evaporates and enters the atmosphere as water vapor. And then when that water vapor condenses, it releases a lot of heat energy. And then the atmosphere mixes. And so you see basically that kind of that cloudy like is actually water vapor, but it's mostly in the tropics. And then it needs some way, that energy just can't go straight to the poles. It needs to mix. And so those are our storms. And so storms have a role in the climate system of mixing the heat energy from the tropics to the high latitudes. And the job of climate, let's say, is to maintain energy balance, that there has to be the same amount of energy coming into the planet as leaving. And the role of the atmosphere is to mix that heat energy. The ocean also has a role to transport heat energy polewards. But mostly the way we conceptualize the Earth is that it has many different pathways to bring that heat energy up. And if one kind of slacks off a bit, usually what we expect is that the other part will intensify. Next slide. So when thinking about problems in the geosciences, they're all kind of complex. There's these large scale systems, and there's all these details. And scientific advances are driven by kind of two types of ways of thinking. One is through observations, and you need observations of the entire system. Or let's say Greenland, the Greenland ice core record is thought to be representative of a large area of the Arctic, the whole Arctic, that you can't necessarily change Greenland independent of other places. And you also need observations of small details, like planes flying through clouds and making observations of droplets and how droplets coagulate and form crystals and the like. Also, the advances are driven by models, comprehensive, large-scale models of the Earth system that kind of integrate together all this knowledge from all these details. We also need conceptual models because these large-scale models are too complicated. We can't really understand cause and effect without having some sort of way of simplifying what's going on. So these are the characteristics of the geosciences. Next slide. So this type of thinking, which you have a large-scale behavior and the details and their interaction, is also, like say, a type of consideration that takes place with phase transitions. So this, I'm going to go through an example of a phase transition that I did with my son when he was in 4th grade. We had a science fair project, and he was interested in crystals. And we had the question of whether we could, in our garage, form another phase of ice. So if you look at this figure, on the left-hand side, it's temperature, and as you cool, like basically liquid water, that becomes ice 1. So that's the ice that we experience. But as you add pressure, that ice can form different phases. And what a phase is in this case is an arrangement of the atoms of the water molecule. And those arrangements can take on different configurations. And so, for instance, the density of water is about 1 gram per centimeter cubed. When you go to ice, it's less dense than water, so it floats, right? So it has about 0.92 grams per centimeter cubed. But ice 2 that we wanted to form has 1.17 grams per centimeter cubed. And so in order to generate this, we had to cool it down. And for that, we had a bath of alcohol and dry ice that brought this bath down to negative 78 degrees Celsius. And we had a car jack. Yes, let's go on to the next slide. We have this car jack that lifts up a car, and we're going to squeeze ice between these two steel trays and try to add pressure. And the pressure we needed was about 400 megapascals. The pressure underneath the Greenland ice sheet, Greenland and Antarctica is about 30 megapascals. So we need to have many times that amount of pressure. And so ice 2 doesn't really exist naturally on Earth. So we created this tray, and we advance the slide. We put 2 drops of water in a little cup. Next slide. And then we put it in this contraption where that water froze, and we measured the distance between 2 steel plates, and we kept on squeezing this water until eventually, basically, there was this phase transition, and all of a sudden there was this loud boom, and the whole ice collapsed on itself. So it was really dramatic. Next slide. So the density of ice was also given by the thickness between these 2 plates, and we started at something near around 2 millimeters. And as we added pressure, basically at the point where we had that sudden loud bang, basically the whole column collapsed down a certain fraction. And so that meant that the density of that ice increased to much more, and we figured we had ice 2. Next slide, please. That's what it looks like actually after we take it out. I don't know if that's actually ice 2, because it might have rebounded basically back to ice 1. But the point here is that the arrangement of those atoms, they rearranged themselves such that new bonds formed. And that was a distinct pattern. And so that's the ability to predict this is based on the angle that's made between the oxygen atom and the hydrogen atoms, and that because it has a certain angle, it allows for that substance to have all these different properties. And that as you add pressure, it can take on different arrangements of these crystals. And so it's a fundamental property of the water molecule to take on all these things. And so one of the questions we have about abrupt climate change is that what is the property of the Earth system that allows for these abrupt changes in the basically delivery of heat from the tropics to the poles? Next slide. So people have one idea. Oh, I see. If somebody could tell me how much time I have left. Probably not much, right? But anyway, I'm almost done. There's basically an idea that we have, and I would say it's good, but it doesn't explain everything. One is that it happened during the last ice age because we have these ice sheets. They collapsed, and it led to a reorganization of ocean circulation. Next slide. Ice sheets are mostly can sit very tall in the atmosphere. However, they accumulate a heat at the base because of geothermal heating, and that heat can accumulate, and all of a sudden you have something that was once frozen to the bed become thawed, and then all this ice can basically slide out into the ocean and create these icebergs and change ocean salinity. So next slide. The ocean basically delivers heat to the north. This warm, salty water from the tropics comes up to high latitudes, it cools, and because it's salty, it sinks deep into the ocean. And that helps bring basically this warm water to the pole. But if you add a lot of fresh water, it interrupts the ability of that water to sink. And therefore, basically the ocean's role in delivering heat. So we think this was involved in these events. Next slide. And one evidence of this is the ice core data showing the proxy for air temperature with higher is warmer, but now time is going to the left, going from about 52,000 years ago to 26. And wherever you have this this hash marks is where we have evidence of ice sheet collapse in the, and that's through basically these icebergs carrying rocks from the middle of the continent out into the middle of the ocean. Next slide. So ocean sediment normally is made up of all these like little shells, but where we find these events that where it's really cold, you see this ice rafted debris, meaning it was rafted, it was incorporated into icebergs, brought out into the middle of the ocean where it melted, and it sprinkled the bottom of the ocean with these rocks. These are crystalline rocks that are only found on the continents, not usually out in the middle of the ocean. So that was our evidence that icebergs and flooding the ocean actually happened. Next slide. Okay, so this is my final slide. So kind of broadly speaking, we see that the Greenland ice core proxy for air temperature shows abrupt climate change happen repeatedly. We don't understand how these events that occurred in the North Atlantic impacted global climate, which they did. So there's still some outstanding questions. So there's probably other components of the system that have this kind of threshold behavior, in particular the tropics. People really want to know how the tropics, this interplay between taking the sun's energy, evaporating into water vapor, collecting it into water droplets, that takes place through these storms, tropical storms. But the organization of tropical storms is really complicated. So, so the question is, are there phase transitions in tropical climate? And that's the type of question that I'm interested in now. So I think I'll stop there, and if people have questions, I can take them.
Thank you so much, Dr. Jackson. That was wonderful. I'll read some of our question submissions for you. So from Michelle, we've got, what compelled you to become a geophysicist as a child?
Not as a child. I guess when I was interested in physics, I like conceptual fantasies. So for instance, Star Trek, you know, the ability to travel the speed of light, what does that take? And physics had all this basically conceptually rich questions. And so and as a physics major at undergraduate, I didn't actually care what type of problem that I worked on. I just like problems, puzzles, if you will. And one of the things I like about geosciences is that there are lots of questions, and they're really interesting questions. And I was concerned if I stayed in physics that I wasn't clever enough to ask really good questions. But when it's in the geosciences, it's actually pretty easy to ask good questions.
Thank you so much for your answer. That's really cool to hear about how the puzzles led you to find this really niche career path that's like perfect and well suited for you. I'm also a Star Trek fan, so shout out for that. I love Star Trek and Star Wars. All right, then we've got, are there any books or resources you would recommend for reading up on the science of climate change or geophysics?
Okay, so there's a book about abrupt climate change. It's called The 2 Mile Time Machine. It's by Richard Alley. And Richard Alley is one of the principal investigators for the Greenland ice sheet ice core. He's also on the National Academy of Sciences, and he has this wonderful ability to describe science in really compelling ways. And almost anything that I think he has stuff online that describes the climate system. And I would basically look for anything that he does. This is Richard Alley. and that's a book that I've given my dad, and my dad's a big kind of loves following this stuff. There's another book that I recommend that is very different, and this came out in October, and this is The Ministry of the Future, and this is fiction. And this is by Kim Stanley Robinson, and he wrote the Red Mars trilogy. And he's kind of a science fiction writer that likes to do things in more realistic type of ways. And what he's done is think about the way climate change will impact society, and wrote a kind of a scenario of how we will be confronted by the challenges of climate, in from both science and politics, the economy. Almost everything gets impacted. And this kind of book plays out these basically scenarios. It's anyway, it's an intense book.
Thank you so much. Those are wonderful. And I'll post both of those on our Instagram stories later tonight so people can review those, because those sounds like great reads. So thank you so much. Last question we had, what are some skills you think are going to be most useful for future scientists to have in general and in your field?
Okay, so a lot of sciences, they love rigor, and there's a lot of new possibilities with kind of data sciences, analyzing data. How do you interpret data, especially very complex data? So the geosciences have a lot of complex data, and part of that is the role of the model, the simplified thinking in interpreting that data. And so there's all these skills involved with statistical and or theory, and how that plays into making sense of very complex data. And this actually puts you in good stand for like almost any type of career, but it's particularly important for the geosciences that are very data driven, with satellites and new types of measurement possibilities with sensors in your phone and everything. And we need to basically make use of any and every way of collecting data to understand basically the relationships that exist between the forcing and a response.
Thank you so much for answering those questions. Those are so detailed and really helpful for all of our younger scientists in the room, or in the room on the screen. Thank you so much for your time and for coming to speak to everyone here. We were so excited to have you, and you took support in this event. And your talk was wonderful and very fascinating. So thank you for teaching us about abrupt climate change today. It's wonderful seeing you. Yeah. Thanks again for coming. So now I'll hand it off to Isha Borker to introduce our next speaker.
Thank you, Dr. Jackson and Becca. Hi, everyone. My name is Isha, and I'll be your other MC for tonight. Just a reminder, feel free to ask questions. The YouTube in the YouTube description, there should be a Google form link. So feel free to use that and ask questions throughout the presentation. Our next speaker is Dr. Pasalakwa, an associate professor at the Cockrell School of Engineering. Her research interests lie at the intersection of water resource engineering, hydrologic sciences, and geomorphology. Her team's goal is to advance the understanding of how topographic patterns arise, evolve, and interact with the climate and ecosystems. So without further ado, let's give a warm welcome to Dr. Pasalacqua.
Thank you so much, Isha. Thank you all for the invitation and for attending the event. Great Q&A already, and thanks to Charles for a wonderful talk. So I look forward to continuing the speaker session. So this is actually a question that Michelle just asked to Charles, and it's a question that I get very often, because sometimes when you see us in the role that we have, you may think that we got it all figured out, that that's what we always wanted to do, and in some cases that's true. But I wanted kind of to take an opportunity to tell you how I became an engineer, and also I'll take the opportunity to tell you also what an engineer like me does. So water resources engineering actually sits within civil engineering. My training, though, it's mixed between environmental and civil engineering. So I just call myself a water resources engineer. Now, the thing is, my name some of you may know, actually means the water passes. So acqua is water in Italian, and pass is to pass. And actually, that's what I work on. So I work on water and how water flows through landscapes. But I can tell you that, so if you hear that name, you may think, oh, she always wanted to do that. And that's not true. So next, please. And the reason why I think I didn't know, it's because, first of all, I'm a first generation college student. So that means that my parents did not have an opportunity to study. I was born in Italy, and actually you see a map there in the middle. That red mark is the region where I was born, and I was born in a small town with a few thousand people that you see in the picture above, kind of in the center of that arch, so on the Mediterranean coast. My mom ran a grocery store, so she sold fruit and vegetables in a place very close to my school. My dad was a worker in a company that was producing electricity. So I essentially spent my childhood going to school in this little town, and then I would go to my mom's grocery store and do homework. And I would spend my summers at the coast, right? So we would spend our summers on the beach. That was so easy as kids. We learned how to swim very, very early, and we grew up here. So we grew up kind of outside and spending time swimming. Now, the last picture that you see on the bottom right, that's actually my undergraduate institution. So it's actually a beautiful villa where environmental engineering was, and other types of engineering were located. But to be honest, when I was a kid, the first idea that I had was to become a lawyer. And I can't tell you where that came from, but I think that was an early recognition of the fact that I would love to become a teacher. I think I like the idea of giving speeches, of talking, of doing things like that. But when it was come, so when I was in high school, when I was in middle school, in high school, I kind of liked a lot of things. So certainly I liked math and science, but I also liked literature, I liked arts, I loved philosophy. So my interests were pretty broad. But there were two things, though, that growing up, I think marked me or became passions. Next, please. One of them, can you go to the next slide? There it is. So one of them is sea waves. And I think that's because that's where I was born. So I just love waves. And these are motions that you see in the sea, in the ocean, in large lakes, driven by wind, right? And so I grew up with a fascination for these patterns. And also kind of, I learned, because we lived close to the coast and close to water, I started understanding wind patterns. So I started understanding which winds were in our region. That's typical for people that live at the coast. You know which wind it is, you know which weather is gonna bring, you know what weather is gonna look like because of that wind pattern. And so this is a passion that I had, something that I just, to this day, just love watching. So I just love seeing rolling waves. I find it fascinating, kind of relaxing, and sometimes there's huge storms though, right? And so I started getting an understanding that waves are actually one of the agents, right? One of the forcings that shape the coast. And so you see different shapes because also of waves. The other thing that marked me as a kid, and you can go to the next slide, this is less happy, this is flooding. So as in Austin, where we have big storms, and we have had several recent big storms, Genova, the city close to where I grew up, experiences very large events. So these are events, you know, normally the interesting thing is that people always move next to water because we need water, right? It's a resource, and also for soils, for growing foods and things like that. But we like to control water, right? So we'll move next to the rivers, and we want rivers to stay where they are. But that's not the way how naturally things happen, because when you have large rainfall events, as we experience often here, if you have a lot of water that gets in the river naturally will expand to the surrounding landscape. Right? That's how it normally works. The problems, though, is that we live there, right? We don't like that. So we don't want the river to expand because we are in danger, right? And so the city where I'm from, and it happens everywhere, control the rivers a lot. In some cases, actually, the rivers are underneath roads because a lot of people, there's a lot of space because of that region is squeezed between mountains and the coast. And so we needed places to build, right? And so historically, that's what people did. They just cover rivers, they just let them get out of the bay and then use that space. But it's not enough when the river becomes really large and there's a lot of rain, and that creates issues. So, and it's very dangerous. So as a kid, what happened is that I was actually trapped into one of these events. And I still remember it very well. I had gone to the stadium to watch a soccer game with my dad. And during that event, there was this huge rainfall event that kept on coming down and coming down and coming down. And the city infrastructure just started failing. The car that was supposed to bring us home couldn't go through, should never drive with water. And so I found myself, I have memories of walking in the street with this muddy water to my knees and being extremely worried, both myself and my dad. And those two things marked me a lot. And I can't tell you actually that I became an engineer because of that. But I can tell you that these two things, coastal processes and inundation, are two of the main topics I'm working on as a professor. And I am sure it comes from that. It comes from the fact that these are passions or fears that I developed through experience. And I decided to spend time working on them. Now, what a civil engineer does, so a civil engineer is what is called an engineer for society. So civil engineers really work at this interface or interaction of people with landscape. And so lots of the work that we do actually is about human interaction with landscapes, and then cities, and then civil infrastructure and so forth. Next. And so here is an example. All right, so we're going to start with a few examples at the coast, and then I'll talk to you a little bit more about some of the flooding work that we're doing. This is coastal Louisiana, and some of the work actually that we do, or some of the problems, let's say, that are on this coast, are very similar to problems that we have in the coast of Texas. So the map that you see at the top, that shows you an evolution through time, or a result through images, through data, through models of what the coastal Louisiana has become through time. So that refers to a time period between the 1930s and recent time, 2016. So everything that you see in red is land that is not there anymore, all right? And that is a result of a number of factors, but also of what we have done to the landscape, right? So again, we like to live next to the water, but we like to control the water. And through those modifications and controls, the landscape responds. It takes some time, but it will respond. And so in this case, what happened is that all these constraints, walls, levees, flood protections, which are perfectly reasonable, kind of had an effect on the landscape behavior. And so this land essentially has disappeared and has been lost to water. Now, this is very important because not only is land that is gone, but it's also very dangerous when hurricanes come through. So when big events come through, these wetlands, these lands that are exposed at the coast help us, right, kind of dissipate that energy. So they help protect the cities that are behind. But when this land is gone, as it is here, it puts a much higher danger the cities and the communities that leave behind. And so some of the work that we do then is in understanding what can be done about it, right? So we try to learn from landscapes how they form and how they respond through time to waves, to changes in sea level, to the climate shifts that Dr. Jackson, for example, was discussing, and kind of learn from it and try to engineer now in a new way. This doesn't used to be the past. This didn't used to be engineered 50 years ago or 100 years ago, but it's certain engineering of today, in which we understand, we work with the landscape, and we try to leverage how the landscape works so that we create what are called nature-based engineering solutions. So the engineering that are more compatible with what the environment does, so we can coexist better. So what you see below, for example, is the image that you see, the blue one. It's a satellite image. So this is imagery from satellites. And that depicts a portion of the landscape that maybe if you look at the map very closely and you look at the left, the very left part, you see these two deltas, they're called. They're kind of greenish. So these are a few areas of the coast that have been growing land. And so part of the work that we do is to study these areas that have been growing, understand how they works, and then take field observations. So for example, the picture on the right is me and one of my graduate students in the field, trying to understand how the system works and getting data. And then these data can be used to improve models. And those models, similar to what Dr. Jackson was discussing, you can take actually those climate predictions that he will study and use them as input to these models to understand what are we going to see in the next 50, 100 years? Can we still live here? And what can be done to make sure that the landscape is sustainable and we can be safe? Next. Similar problems exist elsewhere. So as I said, and not only the coast of Texas is eroding and is affected by these events, but my work has also brought me abroad. And so this is Bangladesh, which is a country close to India. And it's a beautiful river system, which is called the Ganges-Brahmaputra system. And again, this has been very modified. And so what you see at the bottom is a picture that I took from one of the places where people live, again, in between rivers, so controlled. And that has created problems because elevation essentially has been dropping. And as you saw also from Dr. Jackson, there's this climate change. So sea level is going up, land is going down. So that puts you a higher risk of flooding when you are on the landscape. And the picture that you see, well, the one on the left, of course, is me on a boat because it's a huge system. So we actually traveled in a science cruise, which was wonderful, with a team of not only engineers, but geoscientists, economists, social scientists, all together, ecologists, because these problems are problems that need to be solved across disciplines. And what you see on the right is, again, what we can see from satellite imagery. So it's very much of a mixture between going to the field, seeing where people live, understanding the communities, understanding their needs, and then we can use data from satellite, data from models to understand, is this landscape going to be able to respond in a safe way to the changes that we're going to see in climate, for example, in the next 50, 100 years, and what can be done to manage the landscapes in such a way that it's safe. Next. I'll take you through some of the flooding now. So as I said, one of the fears that I had is flooding inundation. So this flooding that comes from extreme events. And so when I started working here on these issues, it was clear that, and this is true for other parts of the world and parts of the United States, not always you know what is going to flood. So what you see on the left is what is called a flood inundation map. That means that anywhere you live, well, if these maps are available, you can go online, put your address and say, what are my chances of being flooded for a given year? Usually if you're in a flat area, low terrain, so low elevation next to the water, your risks are going to be higher. Now, what do you need to know that? For a number of reasons. For your own safety, of course, to understand how at risk you are, but also if you are designing, like engineers do, structures and things like that, we need to know what magnitude, how big these events might be, and how frequent they are. And again, things are changing because of climate change. But the interesting thing is that lots of areas don't have any of these information, all right? And so when a disaster happens and there's a prediction of rainfall, there's actually no idea, you have no idea what's gonna flood or not based on what has happened in the past. So how are these maps created? There's various ways of doing that, but they have some commonalities. First of all, you need a prediction, an hydrological prediction. That simply means that I need to know how much it's gonna rain, and I need to know based on that rain, how much water am I gonna see in the river. There's different types of flooding right now. I'm gonna discuss flooding from the river. So once you have the prediction, you need to know terrain, because flooding from a river, as I was describing before, happens because you have rainfall or you have water coming from other locations that are before you. So they're sending water towards you. The water in the river, the level in the river gets higher and higher. And at some point, it just passes the limits, the banks, so the sides of the river, and it starts expanding on the terrain. So in order for us to know how far the water is going to go, we need to know how high you are, right? So if the water expands and I have a mountain, if you're on top of the mountain, you're very safe. But if the water expands and you're in a flat area, then you are at risk of inundation. We need to know where the rivers are. So the so-called river network. Rivers are organized in beautiful drainage networks that have particular properties that we study, and we leverage those to improve our predictions. And then you need a mapping approach. This can be done, which means essentially based on how much water I have, where is the water going to go, how far, and how deep. I'm sure you guys remember Harvey, that happened a few years ago, right? I'm sure you know of people that got flooded. That's the problem that we're trying to address. And that's because despite all the work that we have done, even during Harvey, knowing how much water and where it was going to go was a difficult question to answer. So the work that we're doing these days is to translate what we do in research into tools that firefighter can use during an emergency. And not you guys, because when it's flooding, I need you to stay in a safe place and not go around. But emergency responders that manage, so like firefighters that manage the event, need to have more information than they had, for example, during Harvey. Next. So how is this going to work? For example, this is aerial imagery, all right? We have these data. Maybe if you look closely, you can see there's a river in there, but it's not that easy. But now if we do next one more time, this is, by the way, Onion Creek part, so it's local. Now this is a terrain elevation data, all right? So these can be acquired in various ways. The one that you see is usually acquired from a plane. There's a light pulse that is sent to the terrain, and by measuring the response time, we can get a sense of how high the terrain is. So what you see in greenish, you can see the river, first of all, now very well. And what you see greenish around it, it's pretty flat. And then as you go towards the gray, the reds and the gray, it actually gets higher elevation. So you can already think about this river flooding, and you probably can already envision where the areas are going to be more at risk, right? So if you're close to the river and the flood area, you're probably going to see water. If you're higher up, you're probably going to stay dry. Next. So some of the tools that we have developed then, what they do. So what do? They trace the rivers. So what you see there is like what we call the center line. It's a mark of where the center of the river is. Why do we need that? So first, the river has a width. But for some of these analyses, we just need to know where the center is, how deep it is, so that when we know how much volume per time is coming through the river, then we can get a prediction of how high the water is going to be. And then we just take that height, send it to the terrain, and obtain these maps, right? Where it's darker blue, it's deeper and inundated. When it's lighter color, it's actually dry. Now, these maps can be produced very fast. We have them already for various areas. And the beauty of it is that we've developed an application. And if you go next, we can see that. It's an application that is called Pin to Flood, which is in the next slide. And what that does is that it allows the emergency responders to have these maps on tablets, all right? So the biggest thing when you have flood events, yes, please, Rebecca. The biggest thing when you have flood events, maybe it's not loading because it's not changing, but in the meantime, I can talk. There isn't much more to this. There it is. Okay, so the biggest issue with these events to manage is that if you're a firefighter and you go out, for example, at night and it's raining, you have no idea how wide this flood is. You have no clue because it's very hard to predict. But what we do is to provide these maps, and what you see as the red dots, those are pins that a firefighter can draw. So they can say, okay, they can say there's water here. And based on that, our precompiled maps give them a sense of what's the likely extent of that flood. And that way they can dispatch resources, they know which neighbors are at risk, They know how deep the water is going to be, so they know if they need a boat or if they need a car and things like that. So there's maps that kind of directly translated from research into tools that in a few seconds can give information that hopefully is going to help save lives, because right now these tools are not available. I think this is almost the last slide, so I'm going to go next. And I'm going to show you a beautiful piece of art that a young artist whose name is Champ Turner. He just started college this year. He actually graduated high school here in Austin. He collaborated with us and with a larger group at the University of Texas that I would like to advertise, which is called Planet Texas 2050. This is an initiative that bridges barriers. So as you see, there's a lot of disciplines here involved. There's not only an engineer that does this alone, but there's a lot of collaboration across disciplines, including the arts. The arts are a beautiful way to communicate scientific results to the public, but also I think this drawing really encapsulates what I want you to be left with this message, is the fact that we coexist with landscapes and water behavior. And as humans, we've modified these landscapes. But what we're doing now is really to make sure we manage landscapes in such a way that they can function naturally and we can live there in a way that is sustainable and possibly respond in a safe way to the events that we're going to see in the future. And with that, I would like to thank you for your attention. I'll take any questions, of course, that you might have.
Yes, thank you, Dr. Pasalacqua. That was amazing. I never knew there were so many like research methods that you could use to like detect water, which was really fascinating to hear about. So the first question is from Rudy in El Paso. They asked, do you work with NASA to acquire the LiDAR and satellite imagery in order to study bodies of water?
Yeah, I do actually. Beautiful question. Yeah, we're really thankful in this country because worldwide, because we have access to what is called remotely sensed data. So as you saw, it's very interesting because landscapes are large, right? So when you go in the field, there's this much you can do. Like you can detect some information here and there, particularly at the coast, conditions change very fast. And so you can't be with the boat everywhere. I mean, you could, you need just a lot of money. And so remote sensing is beautiful because it allows you to see landscapes. And so we actually have various ways of interacting with the USGS, with NASA, but actually I have an active project right now, which is called Delta X. And actually, if you go on my website, it's linked from there. Actually, the planes are in the field right now. That's a new mission that is funded by NASA. And I'm one of the science team members. There's other 7 institutions involved. Again, very cross-disciplinary. And the beautiful thing is that we're trying to understand water level fluctuations from various instruments that right now are prototypes of future satellite missions. These are prototypes in terms of on airplanes. And so we're collecting field observations. I'm doing modeling. I'm one of the modelers with my team. And there's data from airplanes. And this is to, again, get a better understanding of coastlines and of coastal systems and make better prediction for the future.
That's awesome. And we'll definitely link that in our Instagram and our social media.
Great.
Yeah, definitely check it out. That sounds really cool. Another question from Rudy in El Paso. They ask, apart from remote sensing, how else do you study water?
Yeah, so it's, again, great questions, because I think lots of us will say it's a combination of methods, right? So, and sometimes when you study, when I did my PhD, for example, when I was in graduate school, I was mainly remote sensing and math. So I was looking at data on my screen and I was running models. And as I continued with this research, I really come to appreciate going into the field, because it's very hard to model a landscape that you've never seen, right? I mean, sometimes you try to understand what is the vegetation going to do, well, you need to know how the plants even look like. And so these days, I do a little bit of everything. So we go in the field and take observations, which is really important for understanding our models and improving our models. We run numerical models, so we rely on computational capabilities and essentially mathematical expressions to mimic what the water and the sediment do and how landscapes evolve. We use remote sensing. And then the fourth thing would be experiments. I don't do experiments myself. but I have a lot of colleagues here at UT and in other institutions that do. So we often also do experimental results. Because again, what you need is the challenge is a wide range of scales, right? Channels can be a few meters wide and they can be kilometers wide. And processes can be instantaneous because water moves right at any moment, but it can also be geological timescales, which is more like what Charles was discussing. You can't encapsulate it all. And so through these variety of tools together, that's where the solutions come from. And so various tools are more appropriate at different scales, but they all really talk to each other. In fact, AltaX, the campaign that I was mentioning, uses them all because they're really all needed and they all feed back into each other.
Thank you so much. It is really cool to see how many like technological innovations can help us gather so much data. It's really cool. We have a question that asks, what advice do you have for a girl who wants to have a career in STEM and potentially in something civil engineering or environment related?
Yeah, I would say go for it. That's beautiful. I had a great time always, and I have to say I went through engineering when there were very few women. That's not the case anymore. My classes are easily 50-50, you know, and on the faculty we're also very balanced, so things have changed. When I went through engineering, yeah, were less women, but it didn't really matter. I enjoyed it anyway. It's nice to see the more balanced environment. I would say my recommendation is really follow your curiosity and follow your passions and never be afraid of asking those questions or being wrong. And that's something that I struggle with a lot, partly because I was always afraid of asking questions. I was always afraid of putting myself out there because I was afraid to be wrong. And it just came to the point that if I wanted to do something new, I couldn't be worried about being wrong, because if you're always right, you're probably doing the wrong thing or somebody's already studied before you. So I would just say take ownership of it. It's if you're driven to do that, I think it's wonderful because there's so many things to study. Like this is an example of what I'm doing, but there's so many wonderful things to study. And you have an opportunity to really do something for others and make a change. And I would definitely go for it. And I think you will enjoy a lot. And I would also say, and I think that's true for, for any person in my role, if we can help, I'm easy to find. My last name is very unique. Just send me an email. I'll be happy to provide any advice or help out through time.
Thank you so much, Dr. Pasalakwa. That was great advice. Definitely do STEM. The STEM is it's a great career path, really interesting. And with that, I think we will end our speaker section. Thank you, Dr. Jackson, and thank you, Dr. Pasalakwa.
Thank you, guys.
Yes, that was an amazing speaker section that we had tonight. And we will just take a short break and then we will come back with Division B and Division C for your awards. Thank you guys so much. We'll see.
welcome back, everybody. Now we'll begin the awards ceremony. Thanks again to our wonderful speakers for coming out to talk to us. We'll go to the next slide to start us off. Again, for those of you just tuning in, check out our social media pages. We've got a TikTok at ATX Scioli. We'll start posting videos of our team so you can get to know us. And we also do member spotlights on Instagram, so go check that out. Our Instagram is also at atx.scioli. We have we'll go to the next page. We also have a spring giveaway contest going on right now, and you're eligible to enter today, and the winner will be announced tomorrow. You need to follow our Instagram at atx.scioli, repost this image in your story, and tag a friend in the comments to be entered. So we'll have some UT merch for you, so stay tuned and look forward to that. I'll go to the next slide. This is our wonderful team. Isha and I will be your MCs for tonight. But this is everyone also behind the scenes and everyone else working to bring you this event. Thank you guys so much for coming out to compete. We're really grateful to have a tournament out here for you guys. So yeah, I'll hand it off. Next slide. I'll introduce Ashish first, and then our president, and then he can introduce our tournament directors. I'll hand it off to Ashish now.
Thanks so much, Becca. Could y'all go back one slide? Thanks so much. Yeah, so I just really want to say a huge thank you to our team. Right before that, though, just emphasizing, definitely go enter that giveaway, because I think we only have 14 people, so there are great odds of getting some free UT merchandise mailed to you. So definitely go check out our Instagram page, follow us, and yeah. So yeah, first of all, I want to thank everybody for coming today. I want to thank our team for doing such a great job. I'm really proud of us for adapting to this year's challenges when it came to running a virtual tournament, when it came to moving our whole organization online, our meetings and everything like that. It was a big change of pace for us, but we were adaptable and we were resilient. And I'm just so proud of our team for pulling all of this off. Besides that, I also want to plug, our tournament directors next will talk to you a little bit more about tournament and everything, but I do want to plug a little bit of our outreach division. They won't be presenting today, but we definitely run a yearly coaches clinic to support our coaches in about September, so please be on the lookout for that. We also have been mentoring students at schools in Science Olympiad topics and are very, very interested in starting up new Science Olympiad teams. So if you know any schools who want to start new Science Olympiad teams, or if you yourself are, a new Science Olympiad team who needs support and mentorship, we have a lot of people here who are willing to help. We've even been fundraising to potentially support some new schools with materials or travel costs. So please reach out to us. We are so, more than happy to see how we can help. Besides that, I just wanted to say, join us. If you're coming to the UT or if you're considering applying, do apply in future years. But I know a lot of us haven't really, a lot of y'all who are seniors may not have figured out where you're going to college, but if you're coming here, we would love to have you. And our recruitment will probably start later this semester, around May and stuff, but it should extend into the early fall. So just be on the lookout for us. We'll try to show up at orientations. We really, really would love to have you as part of our team. It's a really tight-knit community. We love hanging out with each other and having socials. And of course, it's such a rewarding experience to pull this off and give back to the community that, put us where we are today. So I know y'all are very eager to get to awards. First, just a quick word from both of our directors, Anita Rhodes and Aditya Shah. Next slide, please. All right.
Thanks, Ashish. As he said, I'm one of the tournament directors here. My name is Anita. I actually am a former competitor like many of us here. I grew up in Centerville, Ohio, where I did both Division B and C. So I really know what it's like to be in your shoes as competitors, and I'm really glad to be here with you today. On behalf of us, I just want to extend such a tremendous thank you for being here. Running this event is a really meaningful experience for us, and I know it's been an unprecedented and often difficult year. So the fact that you are all here today is really just such an incredible feat, and I hope you are all so proud of yourselves. But above all, I hope you had fun. We had such a blast putting this on for y'all. I hope you were able to learn something, and I hope you're really able to enjoy the tests that we put out. That said, we're always looking for ways to improve. So please fill out our test feedback form. We love hearing your feedback, and we really love learning how to make this event even better for the future. So if you'd like to fill it out, the link went out in a remind message earlier today, and we will also be sending out a follow-up email soon with that relinked. So students, please ask your coaches for that, and coaches, please send that out to your students so we can get your feedback. And just once again, thank you for being here. And I'm gonna hand it off to my co-director now.
Hey everyone, like Anita said, I'm one of the 2 tournament directors for ATX Science Olympiad. In addition to all of the thanks that we've given before, I also want to give a special shout out to Duan Duang, who's the creator of Olympiad. And without him, we probably wouldn't even be able to have all these virtual competitions. Throughout the entire year, he's been supporting not only us, but all of the other competitions by, innovating and adding new features to the website. And his support, both at our invitational and our regional, has been critical to making sure that we can get your exams graded and all of your answers saved. Now, this tournament is a really special moment for me because it reminds me of how old I am. I've been a tournament director for this organization for the past 2 years, and next year I'll retire and become one of our veteran advisors. So this is probably the last tournament that I will ever help out with in my life. I first began Science Olympiad when I was like 12 or 13 years old, so about 9 years ago. And it's been an incredible journey filled with ups and downs, failures and triumphs. So when I decided that I was going to come to UT at the end of my senior year of high school, I reached out to one of my friends that was in college that I knew had done Science Olympiad in high school. And I asked them how to join the UT Science Olympiad organization. And they told me that it was a year or 2 from falling apart, and that, it was crazy and a waste of time and that I just shouldn't do it. And instead of heeding his advice, I decided to join the organization. And I decided that as long as I was at UT, this organization wasn't going to die. So my freshman year, me, Ashish, and the rest of our class of 2022 cohort, we came to this organization, and I could see what my friend was talking about. It really was 1 or 2 or 3 people through their Herculean effort holding everything together. And it was honestly a miracle. Some of those tournaments a year, like 3 or 4 years ago, were even happening. And the growth that our organization has had has really just been absolutely amazing and inspirational. We used to struggle to have teams at our tournaments. Back when I was in high school, some of our tournaments would have like 10 or 15 teams in each division. Our invitational just a couple months ago had nearly 200. We used to struggle to have event supervisors running our events, and now we have people apply for the privilege to be a part of our tournament team. Back when I was a freshman, some of our organization's meetings would have literally like 4 people, so it was barely a meeting to begin with. And now we're up to like 30 or 40 members in good standing, and it's really just been an absolute transformation. All in all, joining this organization has been one of the best things I could have done when I came to college. Science Olympiad has been one incredible journey for me, and it's been an honor and a privilege to be the tournament director for this organization the past 2 years and see all this amazing growth, but not just in our organization, but in the Science Olympiad community in Texas as a whole. I'll never forget this. Thank you so much to all the coaches and the students and the parents for supporting us every step of the way. And if you're a high school student that is thinking about coming to UT, whether you're a senior or a junior or what, you should really join this organization. You won't regret it. With that being said, I know you guys are really waiting for the awards, so let's get to it.
Thank you so much, Anita, Ashish, and Aditya for that wonderful sentiment. I just wanted to give another shout out and just say how cool it has been to be such a part of a well-organized team, and really give another shout out to Anita and Aditya for putting on this wonderful tournament. I used to come to this tournament both in middle school and in high school, and Aditya is actually the one that referred me to this event and was the person that got me interested in joining to begin with. And so I'm really grateful. And as much as we'll miss you, I just wanted to say thank you for the impact you guys have had on this organization so far. So with that, we'll begin the tournament award ceremony slides. Alrighty. For Oh, next slide. Oh, there it goes. For our first event, we have Division C, Anatomy and Physiology. Coming in fourth place, we've got Liberal Arts and Science Academy, LASA B, C11. Liberal Arts and Science Academy, LASA A, C10. In second place, we've got William P. Clements, Clements A, C16. And in first place, we have AAH, Austin Area Homeschoolers, Team A, CO1. For Division B, Anatomy and Physiology, in fourth place, we've got AAH, Austin Area Homeschoolers, B01. In third place, Healing, B6. In second place, Beckendorf Junior High, B team. And in first place, Beckendorf Junior High, A team. Congrats, guys. For Astronomy, Division C, we've got in fourth place, William P. Clements, A team. In third place, Bridgeland, Team 3. In second place, Liberal Arts and Science Academy, LASA Team A. And in first place, Austin Area Homeschoolers, Team A. Yeah. For Division B Botany, we've got in fourth place, Nios Charter School, B11. In third place, Beckendorf Junior High B. In second place, Keeling Middle School. And Beckendorf Junior High A in first place. Congrats, competitors. In Division C Chemistry Lab, we've got fourth place, Summer Creek High School. In third place, Clements B. Second place, the Hockaday School, Team A. And in first place, Clements Team A. Give yourself a round of applause. Division B Circuit Lab. In fourth place, we've got Nios Charter School. Third brings us Keeling Middle School. Second place, Beckendorf Junior High Team B. And in first place, Beckendorf Junior High Team A. Great job. Division C Circuit Lab. In fourth place, Austin Area Homeschoolers Team A. In third, Clements Team B. Second place, Clements Team A. And in first place, Liberal Arts and Science Academy Team A. Congrats, competitors. In Division B Crime Busters, I wrote this test, so I'm really excited to see how y'all did. In fourth place, we've got Beckendorf Junior High B. In third place, Beckendorf Junior High A. Second place, Keeling Middle School. And in first place, Bonham Team B. Oh, sorry, just Bonham. Okay. Team 4. In Division C Codebusters, fourth place, we've got Clements B. In third place, we've got Bridgeland. In second place, we've got Liberal Arts and Science Academy, Team A. And in first place, we've got Clements Team A. Division B Density Lab. In fourth place, we've got Bonham. Third place, Austin Area Homeschoolers. Second place, Keeling Middle School. And in first place, Beckendorf Junior High, Team A. Division C Data Science. In fourth place, we've got Austin Area Homeschoolers, Team A. In third place, William P. Clements, Team A. Second place, Summer Creek High School. And in first place, we've got Liberal Arts Science Academy, Team A. In Division B, Disease Detectives, fourth place brings us Bonham. In third place, we've got Keeling. Second place for this event is Beckendorf Junior High Team B. And in first place, we've got Beckendorf Junior High Team A. Congrats, guys. In Division C, Designer Genes, fourth place is Liberal Arts and Science Academy, Team B. In third place, Austin Area Homeschoolers, Team A. Second place, Liberal Arts and Science Academy, Team A. And in first place, William P. Clements, Team A. we've got Division B, Dynamic Planet. Fun, fun. In fourth place, we've got Keeling Middle School. In third place, Bonham. In second place, Beckendorf Junior High, Team B. And in first place, Beckendorf Junior High, Team A. Alright, in Division C, Disease Detectives, we've got fourth place, William P. Clements, Team B. In third place, Austin Area Homeschoolers, Team A. In second place, Liberal Arts and Science Academy, Team A. And in first place, Clements, Team A. Next up, we've got Division B, Food Science. In fourth place, we've got Bonham. In third place, we've got Austin Area Homeschoolers. Second place brings us Keeling. And first place is Beckendorf Junior High, Team A. Congrats everybody, on to Division C, Dynamic Planet. In fourth place, Clements, Team A. In third place, Tomball High School. In second place, Clements B. In first place, Liberal Arts and Science Academy, Team A. Alright, in Division B, Fossils, fourth place, we've got Nios Charter School. Third place is Keeling. Second place is Beckendorf Junior High, Team B, and in first place, Beckendorf Junior High, Team A. Now I'm going to hand it off to my co-host Isha to carry on from here.
All right, guys, good job so far. So we'll start off with the next event, Division C, Fermi Questions. In fourth place, we have William P. Clements. In third place, we have Liberal Arts and Science Academy, LASA, C11. In second place, we have Clements, C16. And in first place, we have LASA, C10, sorry guys. Division B, Game On. In fourth place, we have Austin Area Homeschoolers. In third place, we have Bonham, B4. In second place, we have Beckendorf Junior High, A. And in first place, we have Keeling. Congrats. In the next event, we have Division C, Forensics. In fourth place, we have LASA A. In third place, we have LASA B. In second place, we have Bridgeland. And in first place, we have Austin Area Homeschoolers, Team A. Woohoo! Good job, guys. Yeah. Division B, Green Generation. In fourth place, we have Beckendorf Junior High B. In third place, we have Bonham. In second place, we have Beckendorf Junior High A. And in first place, we have Keeling. Division C, Fossils. Fourth place, we have LASA B. In third place, Austin Area Homeschoolers, Team A. In second place, Bridgeland, CO3. And first place, we have LASA A. Is Division B, Heredity. In fourth place, we have Keeling. In third place, we have Beckendorf Junior High A. In second place, we have Beckendorf Junior High B. And in first place, we have Bonham, B4. Next event, Division C, Geologic Mapping. In fourth place, we have LASA B. In third place, we have Clements B. In second place, we have Clements High School A. And then in Liberal Arts, we have a LASA A. All right, Division B, Machines. In fourth place, we have Beckendorf Junior High B. In third place, we have Keeling. In second place, we have Bonham. And in first place, we have Beckendorf Junior High A. Division C machines. In fourth place, we have Austin Area Homeschoolers Team A. In third place, we have Clements High School A. In second place, we have Clements High School B. And in first place, we have Lhasa A. Division B Meteorology. In fourth place, we have Bonham B4. In third place, we have Keeling. In second place, we have Beckendorf Junior High B. And in first place, we have Beckendorf Junior High A. Division C Ornithology. In fourth place, we have Austin Area Homeschoolers Team A. In third place, we have North Austin Science Alliance, C12. In second place, we have Lhasa Team A. And in first place, we have Clements High School A. Great job, guys. Division B Ornithology. In fourth place, we have Austin Area Homeschoolers B1. In third place, we have NASA B8. In second place, we have Beckendorf Junior High B. And in first place, we have Beckendorf Junior High A. Division C Protein Modeling. In fourth place, we have Langham Creek, C7. In third place, we have Lhasa A. In second place, we have Bridgeland, C3. And in first place, we have Clements A, C16. Division B, Reach for the Stars. In fourth place, we have Bonham, Team B. In third place, we have Beckendorf Junior High B. In second place, we have Beckendorf Junior High A. And in first place, we have Bonham, B4. Woohoo, great job, guys. Division C, Sounds of Music. In fourth place, we have Summer Creek High School, C24. In third place, we have Clements High School B. In second place, we have Lhasa B, C11. And in first place, we have Clements A, C16. Division B, Rhodes Scholar. In fourth place, we have Beckendorf Junior High B. In third place, we have Bonham B4. In second place, we have Keeling B6. And in first place, we have Beckendorf Junior High A. Division C, Water Quality. In fourth place, we have Liberal Arts and Science Academy, Lhasa B, C11. In third place, we have Clements High School B, C21. In second place, we have Lhasa A, C10. And in first place, we have Clements A, C16. Next event is Division B, Water Quality. In fourth place, we have Keeling, B6. In third place, we have Bonham, B4. In second place, we have Beckendorf Junior High B. And in first place, we have Beckendorf Junior High A. All right, so now we're going into the overall top schools. So in Division C, we have fourth place, Bridgeland High School, C3. Congrats, guys. All right. In third place, we have Austin Area Homeschoolers, C1. Congrats, guys. You guys worked hard for this. Yes. All right, in second place, we have Clements High School C16. Round of applause. We're all clapping for you guys. Woo! And for first place, we have Liberal Arts and Science Academy C10. Congrats to all the competitors. You guys did great. Thank you guys for coming out for Division C overall top schools. And now I'm going to pass it on to Becca to tell us Division B overall top schools.
Thanks, Isha. I'm excited to announce our middle school winners. After this, congrats again to everybody competing and all of our Division C top schools. In fourth place for Division B, we have Austin Area Homeschoolers B1. Give yourselves a round of applause from home. So excited to see all the results. In third place, we've got Bonham B04. Congrats, guys, for completing all the events today. We're all really, really proud of you. In second place, Keeling Middle School B6. Y'all did a wonderful job adapting this year. So yeah, thanks for coming to the regional. Finally, let's give a big drum roll to the first place team, Beckendorf Junior High B2. Congrats, everybody. I'm really excited. We had such a joy putting this on. I'll give you a little round of applause from my home. Finally, to wrap it up, I'll hand it off to Ashish. Oh, but before I do that, make sure to follow us on Instagram and TikTok and enter our giveaway contest because we'd love to see you repping UT merch. And we'd also love to contact us if you're a senior, as we'd love to have you on our team next year. So yeah, thank y'all for coming out, and I'll hand off to Ashish now.
Thanks, Becca. Yeah, I just wanted to say thank you all so much for coming. Big thank you to our team for being able to pull this off. We have two very, very special seniors that are graduating among many who have volunteered with us. And I wanted to give a special shout out to Ivana Wang, who is a civil engineering major who's going to work for a civil engineering firm full-time. I also want to shout out Jay Mutu, who is graduating a year early and who has actually been working with the CDC and hopes to eventually go to medical school. And we are so proud that these seniors have helped us so much over the last few years. And it's really hard to express my gratitude for them and for everybody on this team. It means a lot to us that y'all came out, that y'all believed in us to run this regional and to run our invitational for those of y'all that came. And of course, we hope to see y'all in the future, either at one of our future outreach events like the Coaches Clinic or at our future tournaments. Thank you so much to Becca and Isha for being the MCs. Thank you to our speakers. Thank you to our tournament team for supervising and everything. And thank you to all of you once again for showing up, for bearing with us, and for adapting like we did to the new virtual format of Science Olympiad. We hope to see you back at UT soon. Thank you so much.